no longer by the end of the course, it'll be very rare to consider knots as these things like living in space. You'll just be used to thinking of them as these simple pictures that we manipulate. So it becomes kind of like combinatorial rather than, very topological. All right, so let me draw another example, just to make sure people understand. So here's an example. Right, so think of the plane as very rubbery. If you start with something like this, that's a picture of the unknot. Now I can get different pictures just by distorting it. Right, so maybe you can kind of imagine so the right way to think of it is you're not just moving this loop around, you're moving the thing containing the loop, like the surface of the chalkboard, but the surface of the chalkboard for some reason is highly elastic rubber. Okay? And I guess I can make it more complicated. Alright. There's many kind of complicated pictures I can make just by moving it around. Questions, Luke?
But so if you were to rearrange it in such a way that, like, you can't, okay, if you were to rearrange it in such a way that something, overlapped something else, right?
You don't want to do that.
No, I know, but then does it cease to be the same knot? Like, does it, like, if you were just to take that one, like move it a little bit, I guess, when you're looking at it as a projection, I guess, up, then you would, and it would cross paths with one of the lines, but it cease to be the unknot.
Oh, so you're talking about, like, in space, if I have a knot that projects to something, and I'm moving the knot around?
Like, okay, so you've shown that these are still the same knots. I mean, it's still the same unknot.
Right.
But you just kind of messed it up in this way, but it's
right.
still, but if you were to, make a cross, like if you were to, like, cross pass at something, then would it not be the unknot anymore?
Right, so I guess but the thing is, say the trefoil, right, we're going to find out it's not the unknot. So it's going to be knotted.
Right.
When something's not the unknot, we're going to say it's knotted. And the trefoil, we can sort of make it we can sort of, if we are allowed to sort of move it around, right, and get some curve, we could get the curve for sort of a projection of the trefoil. But the thing is, remember, knot projection has information about overcrossings and undercrossings. You don't just get that by, like, manipulating a loop around on the plane. That's like three-dimensional information. Does that make sense?
I think so.
Does that answer your question?
Yeah.
Okay, so I think one thing I want to point out, though, is kind of related to what Luke was asking, is if you imagine the knots that correspond to the pictures here, the deformation of the plane here actually gives you a deformation of the three-dimensional space also. If you imagine something projecting like this, and there's just a loop here, if every time I move the plane around, I can imagine there's a stick perpendicular to the plane, and I'm moving all the sticks around. And the points that hit the sticks, which are the knot in 3 space, that gets moved around too. So pictures in the plane getting deformed actually correspond to pictures of the knot getting moved around, but in a very stupid kind of way, where, of course, there's more complicated ways to move the knot around that actually changes the pictures by creating self-intersections and removing self-intersections. So we're going to get to that. It's kind of, right now we're just trying to live in a two-dimensional world here. Okay, so the important note about what's going on here is that note the number of crossings. I'm calling these self-intersections crossings. And the underlying arrangement remains the same. This remains invariant, remains the same under planar isotopy. So when we consider these non-projections, we're not really going to consider them to really be different. Like when you look at a picture in the book and it's much nicer looking trefoil than the one I draw, the simple trefoil projection with just the 3 crossings. The books might look nicer, but mine's sort of equivalent up to planar isotopy. So, all right. So let's see here. All right. So now let's talk about Reidemeister moves. So suppose we have 2 knots of the 2 projections of the same knot. Okay. So we're going to start a new topic. Reidemeister moves. You might be like, oh my goodness, what a complicated terms. But unfortunately, this is a person's name, so we can't change that. Reidemeister. As in math, he didn't come up with the moves or come up with the theorem that's named after him, but we venerate we venerate the discoverers by naming it after somebody else. Reidemeister in this case. You had me for algebra. You know this guy Cardano wrote a book and kind of published it for. So Reidemeister, sneaky guy, he published a book on knot theory. Like, I think possibly the first book on knot theory. And so he just like follows a long tradition of people like L'Hopital, who you might have heard about. L'Hopital was kind of meaner, though. He actually got in a contract. He paid some other much more famous mathematician to write the book for him and never revealed that the other guy wrote the book. So in his case, he went a step further. You can do that when you're a marquis. That is pronounced a marquis. Anyways, so suppose we have 2 projections, and we're going to say that it's projections of the same knot. So let's call these projections D1 and D2. So D sub 1 and D sub 2. So after you feel a little bit better, now we're using subscripts and stuff. It feels like we're moving into math land here. All right, so why do I say D1 instead of like say P1, P2? Well, this book's, I like this book, but I noticed the book's a little weird in that most people often use the term diagram instead of projection. But he uses the term projection, so I keep using the term projection, but you should be aware that a lot of people would say instead of not projection, a not diagram. And so since I'm kind of secretly always use that word in my head, even though I say projection, I'm using D. So, but say you have the same, you have 2 diagrams or projections of the same knot. Well, Reidemeister's move, which I'm going to state precisely in a moment, but let's talk about it in a little sort of vague terms. Reidemeister's theorem is going to tells us that there is a sequence of projections. Sequence of modifications that we can make to D. There's a sequence of modifications we can make to D1, which will produce D2. And in particular, these modifications are limited in scope they're only going to affect a small part of the picture and easy to describe. Because so the theorem is going to state more precisely what they are, and once you see what the modifications are, it'll become very clear why they're nice, hopefully. But one thing to note is it's very important what kind of modifications